All right. So I am going to talk today about Compute Express Link and why I think it's awesome and get very excited about it, and talk about how we can use it to deploy persistent, though I should maybe have put the persistent in parenthesis, and we'll get to that in a minute, and acceleration. I am the Chief Technology Officer of a startup that's working on accelerators and computational storage and persistent memory. So if you want to either give us lots of business or buy us for a shit ton of money, just come and talk to me at the end of this talk. All right, so a couple of quotes to begin with. These are not all attributed to me, but I'm not going to say who they are. One of the things that I think happens on a regular basis in the compute industry is we innovate on hardware and we enable new features. But the problem is that, and we were talking about this at breakfast, often hardware developers don't think about the consumability of what they're building. Right? I built this amazing thing, it's a pony, but we have no way of talking to the pony. We have no way of getting work done by the pony. So we need software for that. So often what happens is the software comes along, software gets a bit better, and eventually you get to the point where the software hits the limits of the hardware. And then basically everything repeats because it's all about the hardware. A very good example of that is solid-state drives. So we lived in a world of spinning disks. We were very used to high latency in our I/O, and we were used to these disks being pretty much sequential in and of themselves. Every hard drive was a sequential access device. And then along comes solid-state drives, and suddenly I can have 64 or 128 NAND die on a device, and suddenly my latency is dropped by 2 or 3 orders of magnitude, and my throughput per device has just gone through the roof. And it actually took us quite a bit of time to innovate on the software side with things like taking advantage of multi-core processors, parallel I/O. We're still debating over things like F-Sync and M-Sync and so forth, and it takes a while for the software to catch up. And often there's companies that innovate and make quite a bit of money doing that. In solid-state Fusion I/O, I think deserves to be recognized as a software innovator in that space, right? But there's others that exist. And another thing that happens is that a bunch of hardware vendors get together and start working on a standard. So computational storage or persistent memory or something else. And for a lot of the hardware vendors, software is an afterthought. And some companies are better at this than others, but a lot of the time, a bunch of hardware geeks will work on a standard, and they won't think too much about the software consumption model. And that normally happens to the detriment of adoption. So you end up having a standard that is stamped, it is an official standard, but because it can't be consumed by operating systems, you end up in a world where your standard goes nowhere and nobody makes any money off it. And that's a problem. So that's something that we need to think about. So software is incredibly important. That's one of the reasons why this conference is very interesting, because of the software aspects of it. And so we need to keep that in mind as we work through some of this. I do want everyone, though, to stop and just give themselves a pat on the back. So just do that right now. We've come an incredibly long way, and I just wanted to have a couple of slides kind of talking about this. I have a longer set of slides in this area where I talk about all different things, but we've come a long way, baby. Can anyone tell me what this is a picture of? It's a hard drive. Yeah. Can anyone tell me which company manufactured this hard drive? So, I have a lot of respect for IBM because love them or hate them, they've been around for a long time. Longer than the Christianity, I think, it sometimes. And they'll be around for a long time yet. I think there's a secret message that's given to the CEO of IBM that's passed down from generation that tells them, this is how you survive as a tech company when every other tech company eventually becomes irrelevant, and somehow IBM keep going. So this is a hard drive. This is 1955. It weighed about a ton. You couldn't actually buy them. You had to lease them. But talking to Rob Pegler, he had some numbers, and we reckoned it was about $1 million to own or kind of lease one of these devices. This one is 5 megabytes. Interestingly, a byte wasn't 8 bits, it was 7. God knows. This is from last year. This is a 1 terabyte micro SD card, which you could buy for $500. If you do the math on dollars per gig, we've done a billion-fold improvement, in 65 years. Can you imagine any other any other business sector where there's been a billionfold. Imagine if cars went a billion times faster, or were a billion times more efficient, right? It's incredible what we've managed to do and what we're continuing to do, right? It's very, very exciting, very interesting, but we deserve every once in a while to take a step back from the day-to-day grind and go, we've come a long way, baby. So one of the things I like to think about as we look at technology over time is what I call the biorhythms of computer architecture. So I think over the years, I think everybody realizes that we go through different phases in computer architecture. Sometimes disaggregation makes sense. Sometimes centralization makes sense. And the conjecture that I pose is that that kind of decision, that kind of architecture is dependent on the relative cost of storing a bit, moving a bit, and processing a bit. And the relative cost of those three things with respect to each other changes over time. So we go through phases where computing or processing a bit gets cheaper faster than the other two things. And then we go through another phase where storage changes faster than the other two, and networking. So we can plot those three, and to be honest, I mean, based on the last slide, it shouldn't really be a biorhythm, it should be a biorhythm at an angle, because they're all getting better, right? We don't get worse at any particular thing, but the rate of improvement changes over time. And so relative to each other, the cost of computing a bit, storing a bit, and moving a bit change. And computer architecture, for economic reasons, will change because of that changing ratio. And we're basically living, I turned my mic off. Did it come back? There we go. We're living at a time where processing a bit has kind of stalled for us, right? So Dennard scaling tells me I cannot clock my CPU single-threaded faster. I can't build an 8 gigahertz core. It'll literally blow up. Like literally it'll blow up, right? And Moore's law tells me on a single piece of silicon, I can't put more cores down because my processors, my transistors aren't scaling as quickly as they used to. So my single-threaded performance has stopped because of Dennard. My multi-threaded performance for a single socket has stalled because of Moore's law. And I have a problem with compute, right? On top of that, most of the workloads that are interesting and are making lots of money right now are shit on standard ISAs, right? So AI doesn't work very well on a standard ISA. Image manipulation, image processing doesn't work very well on a standard ISA, right? So you can add special instructions for AI and ML, or you can use a device that's dedicated for that task, which is why we have 7,000 AI chip startups right now, right? Of which one will be successful. You will be successful. All right. So this is why doing the same thing every year doesn't work. This is why computer architecture tends to change over time. This is why we went from distributed systems to consolidation, and why the cloud became inevitable, and why now we're also starting to move to the edge again, right? Because the relative costs are changing. So I've been interested in this area of persistent memory for a while, and the next few slides are actually all old slides. So I'm basically giving this for zero incremental effort on my part. Thank you very much. All right, so beyond NVDIMM, future interfaces for persistent memory. This is 2017. Like I said, we've been at this for a while. I just wanted to take a little step back and go, what do we mean by persistent memory? Right, for me, persistent memory has 3 fundamental attributes. And if you don't have all 3 of these, it's not persistent memory. We got to have low latency, okay? That's not necessarily required, right? I could build you a memory technology that's really, really slow. Slow as fuck, if you excuse my language, right? But it's probably not going to be very successful in the marketplace, right? Memory semantics, so we don't want block I/O, we want byte addressability or cache line. We want something that has a smaller access size than a standard block device. And of course, we probably want persistence, because why would you call it persistent memory if it didn't actually hold your data? So those 3 things are all important. This one is particularly interesting because this is a slide that I really like. Throughput is easy. Latency is hard. So I used to work for PMC Sierra, and then which became Microsemi, which now became Microchip. part of the consolidation world. And one of our business groups was doing hard drive controllers, as in something that controlled many hard drives. So essentially an HBA or a RAID device. And we would sell to customers like Dell EMC, and I would go visit their labs, and they could get tens of gigabytes per second out of hard drives. It wasn't a physics problem, it's an engineering problem. All you need to do is have lots of them. Now, it was interesting because in their lab, the person who calculated the resonant frequency of the chassis was important as the electrical engineer. Because if you have 60 or 80 hard drives all spinning at the same time, that can do some very bad things if they all start resonating together. And I've seen that happen in a Dell lab, and it was, well, EMC at the time, and it was kind of terrifying. Right, so, but throughput is easy. It's an engineering problem. I can just put more things in parallel. And the analogy I give is, think of a highway. If I want to get more cars per second past a given point on a highway, I can just make the highway wider, right? That's not overly hard. That's throughput. I can increase parallelism. Latency, though, latency is a physics problem because time doesn't go backwards unless you're stuck on a plane. Time is relative. Latency is hard. Latency is like saying, I want one particular car to get from one place to another at a very, very high speed, right? Or I want my store command, my load command to respond in a very low amount of time, right? There's certain physical problems that you come up against. The speed of light, for sure, being one, right? So latency is hard, and it's hard even for a car because in order to make a car go faster, I have to worry about aerodynamics, I have to worry about keeping the car on the road, I have to worry about getting power to the wheels, and so you end up building a Veyron, which is a lot harder than building a highway wider, okay? And at some point, you're going to hit some physics limits. We cannot go faster than the speed of light, okay? So we'll come back to that in a minute. So what do we need? What do we need to build this ecosystem? And this is a slide that I've used a few times. And these are some of the things in persistent memory, in the successful deployment of persistent memory, or for that reason, or for that matter, almost any kind of hardware topic. We need a bunch of different pieces in the jigsaw. So we need media and form factors. We need operating system support, which people like Dan and Andy do great work on. We need libraries and tool chains. We have had a few talks on that. We need applications to take advantage of them. We've talked about that. And we actually also need protocols and interconnect. At the hardware level, I need a way of getting my processor to talk to the persistent memory, okay? So I need to have all of these pieces. I'm going to focus today on Compute Express Link, and I wanted to kind of pull out what does Compute Express Link help us define, help us understand in this ecosystem. And I'm going to touch on the fact that it's going to help give some clarity around form factors, and that's a pretty interesting topic. And we talked a little about that at dinner last night, but form factors for persistent memory is a challenge right now. And it's also going to it's also going to address protocols and interconnect. And so CXL has the chance to do all that. Here's another slide. I'm just reusing old slides. This one isn't even mine. This is from Paul Grun, who was at Cray, which is now part of HP, I think, if that deal has closed. I'm not sure if it has or not. But so where can we put persistent memory? You can put persistent memory anywhere you like. But if you want coherent persistent memory, you've got to put it on a coherent bus, okay? As soon as you put persistent memory on a non-coherent bus, even if you then put it on a coherent bus, that link has been broken. That coherency has been gone. And you can get it back with software, but as soon as you say software and coherence, most people are going to shudder, and your application performance is going to suck, and you're never going to want it in the first place. So I will conject that if you're deploying persistent memory, you are almost certainly going to want to deploy it on a coherent interface, and preferably close to the processor, okay? And we'll come to that part in a little bit. So that's a challenge because, for example, there's 13 million servers produced every year, roughly, and there's only two buses I know that are common to absolutely every single one of them, and that's DDR and PCIe. And PCIe is typically not, well, it's not coherent. Let's just say, you can argue a little bit about that, but it's not coherent. So I can't put persistent memory on PCIe because it's not coherent. And I could put it on DDR, and in fact, that's what a lot of people do. That's what we do with NVDIMMs. That's what Optane does in a slightly non-standard form of DDR. But there are some challenges associated with that, and I'll come back to that in a minute. I can put block devices on PCIe, and people are doing that very successfully, and NVM Express is pretty much the de facto protocol for that. I can put persistent memory on an open coherent bus, and I put a few examples there. But if I want to put persistent memory on an open coherent bus, my CPU vendor has to support that bus. And right now, in the markets I care about, Intel own 108% of market share. It's more than 100 because their competitors have to buy Intel servers to build their servers to compete against Intel. So the competition actually makes Intel's market bigger, so they actually have over 100% market share. So that's a problem, right? Because Intel, last time I looked at their data sheets, didn't have an OpenCAPI interface. They don't have a Gen Z interface. They don't have a C6 interface, but they may have a CXL interface. So remember, these slides are from a couple of years ago. So this was my, let's go to the cinema to see what we can see in open coherent buses. So remember, this is a couple of years ago. So there's 3 movies showing right now with regard to coherent buses. There's Gen Z, a new fabric, featuring optical coherency, NVMe support, and scale, coming in 2020, apparently. It's always 2 years out. It's like that remake that never gets made. Yes. Correct. I mean cache coherent. I mean, there is a protocol mechanism by which I can, as a device, can own cache lines. And also, if someone reads from me, there's a cache coherency there with the rest of the system. C6, the ARM Pyre strikes back. So ARM were very, very C6-ish based. AMD also have C6 support. Definitely a very interesting protocol, but again, it doesn't have the support that I'm looking for. And then OpenCAPI, the return of the big blue, return of the Jedi, I don't know, which it was basically an IBM standard that came out. But notice this thing over here, the elephant in the room, the Death Star in the room. Right? And everybody knows that Darth Vader was a big Intel supplier, so we have Intel inside. Don't send this to Intel Legal, please. So there's the Death Star in the room. If I, as a device vendor, want to build and innovate around persistent memory, I need a bus that's supported by my CPU vendor. And the reality is that for the servers that I care about, which are, like I said, 100%, 105% Intel, I don't get this, I can't use this, and I can't use this. This doesn't mean that these are not relevant in the market or they don't have a role to play, but we gotta accept market reality. They're not very useful from a business point of view, right? So all that changed recently with Intel's announcement, along with a bunch of initial promoters for Compute Express Link. So I'll start getting a little more into the details of Compute Express Link in a minute. So you can see some very important names on this list, and there's a mix of different people, right? There's end users like Facebook, right? Facebook build their own hardware, but they don't. They may even make their own chips, but they'll typically buy their application processors from a vendor. And deploy hardware that they buy from other vendors, right? And hopefully from me. I'd love to sell to Facebook, make lots of money. Google, they are very, very similar. So there's quite a few end users here, but there's also hardware vendors and system vendors like Dell EMC and Cisco and so forth. So an interesting mix. These are the initial adopters. There's also members. There's now 75 members, including my company, and other companies can join, and there's different levels of membership. But I think one of the most important things is something that actually happened last week. These 3 companies, as of last week, AMD announced they joined. Mark Papermaster did a blog on it at the weekend. So now, all the processor vendors that I care about, and to be honest, this is the one I really care about, and then these 2 are kind of interesting. But all the CPU vendors that I care about are now CXL members. Does that mean they're going to ship product with CXL interfaces on them? Not necessarily, right? But it's a good start. We cannot say the same for OpenCAPI, C6, or Gen Z, okay? Especially this one, right? And we have to remember that if you want to deploy persistent memory, you need coherency. And if you want coherency, it has to come directly off the CPU. You cannot bridge over PCIe to get coherency. It just doesn't work, okay? So what is CXL? So CXL is kind of like C6 in the sense that it leverages the electricals of PCIe. And that's actually a very interesting thing because Gen Z and CAPI do not do that. They've aligned with the Ethernet kind of SerDes. So what that means is if you've aligned with the different SerDes, it means that things like connectors will not interoperate. So the interesting thing about aligning with PCIe is if you build a server motherboard that has connectors that have been rated for PCIe, they are also rated for CXL, right? So if the insertion loss matches, if the return loss is good, basically if you can plug a PCIe device into your server, in theory, if CXL lives on top of PCIe, that PCIe device could actually also be a CXL device, at least electrically, okay? It also means you can align on things like form factor. So if I have a PCIe form factor that's very popular in the market, that could also be a CXL form factor. So that's interesting in and of itself because right now NVDIMMs are restricted to DDR. That is a very hard form factor to work with. It has very tight requirements on power, on area. Imagine now I can use a PCIe card. Think of all the board area you have there. Think of the power supply. We bring additional power to PCIe cards already in the form of GPUs with additional power. Now I have a huge power budget I can work with. Cooling is much, much easier on the PCIe lanes or on the PCIe cards than it is on the DIMMs. Cooling DIMMs can be a real pain in server design. You have to make lots of trade-offs there, and that can affect how much power those DIMMs are allowed to burn. PCIe, there's a lot more flexibility. I can do things with enclosures and hoods. I can get better airflow. I can move things to the front of the server, to the back of the server. A lot more design options, okay? And all the work that we're doing for PCIe deployment applies for CXL deployment. So U.2, EDSFF, add-in card. These are all standard form factors, and you can also do non-standard. Yes? Correct. Yeah. PCIe does come off the processor. Electrically, so in terms of the baud rate and the signaling speed, they're identical. The protocol that sits on that electrical is very different between the two. So the packet formats and the messaging and so forth are different between the two, but electrically they're the same. Yeah. Correct. Yes. Yes, and there's reasons why that is, okay? And remember, PCIe doesn't, as a standard, doesn't talk at all about the processor complex, right? It's a system agent that lives outside of the PCIe spec. If you want coherence, you have to tie things a little closer together, okay? And that, there's people who will argue there are ways of making PCIe coherent. I don't really want to get into that argument right now. Yes? What do you mean frequency limited? So in other words, is the bus cycle handling multiple cards? No, not on PCI Express there isn't. I think you're in the PCI land, which is very, very old and not at all relevant. Yeah, no. So CXL, basically you can think of it as a new protocol that lives on the same electricals that could be PCIe, right? And so what that allows a processor vendor to do is they can do things like, well, I'm going to build a processor that has, you know, up to 18 PCIe root ports, and you can configure them in the BIOS so they can be by 4s or by 8s. But now I've got a new thing, and you can take 4 of those PCIe root ports and actually upgrade them to CXL root ports, either in the BIOS or potentially even at runtime. Okay, and that's a TBD, but certainly at BIOS time, at boot time, in the BIOS, you could say this root port, and this root port aren't PCIe, they're CXL. And that'll align with certain slots on the motherboard. And you can make that decision as the purchaser of the server, because it may not be locked into the BIOS, it might be a BIOS option. So I can buy a server and I can say, you know what, these 4 lanes are optionally CXL. I don't give a crap about CXL. I want more PCIe. You have that. Or you can say, I really love CXL. I only get, I would like more than 4 ports, but this only supports 4 right now or whatever. I'll turn on all 4 ports and I'll populate them with different CXL devices, right? And that gives us a lot of choice. And electrically, nothing changes. So the server motherboard designer, the people who are slaving away, getting all the insertion losses and the connectors right, their job doesn't get any harder for CXL. And that's very important. And that's not true for OpenCAPI or Gen Z, where the electricals are completely different. So very, very important. The first generation of CXL is going to align to PCIe Gen 5, which is 32 gigabits per second per lane. So 32 gigabits per second per lane, which is 4 times faster than PCIe Gen 3 and twice as fast as PCIe Gen 4, which is only just starting to come out now. Okay, so it's pretty fast. And, obviously there's a roadmap there. Yes? Well, that's a very good question. We'll get to that. So what's the latency? We all said, you saw my slide, right? Throughput is easy. Latency is hard, right? So just to kind of summarize what's on that last slide. That slide is actually an Intel CXL consortium slide, and it's in the public domain. You can get that. So here's some of my takeaways from that slide. PCIe 5 based electrically. Links can be switched via the UEFI, so the BIOS, and perhaps even at runtime, depending on the SoC. All right, so we may not see it in the first generation of processors. We may never see it from given vendors, but other vendors may build an SoC that has CXL support, that supports dynamic switching between PCIe and CXL. I don't know. It may be really hard. It may not work, but it certainly seems like it could be doable. If that is the case, if it can switch at runtime, then we have hot plug. And I can hot plug my NVDIMM into a CXL slot. It will be detected, and the operating system will adopt it via something like memory hot plug. Dan's looking. What? Who's writing the code for this? Yes. Well, we had that discussion yesterday. Initially, I didn't call it an NVDIMM, but Andy says there is no reason why that would not be an NVDIMM. The NVDIMM spec does not state it has to be in a DIMM form factor, as we call it, right? It has to have certain interfaces on the management side, but the spec for an NVDIMM doesn't say it must be DDR or it must be in a DIMM shape. So the interesting thing is it is actually a DIMM. It's a CXL DIMM, right? PCIe connectors and form factors are the same as for CXL connectors and form factors. I think that's really important because as an innovator, an NVDIMM, like a DIMM, doesn't give me a lot of room to innovate. I don't have a lot of power. It's really finicky. And some of my customers don't want to give up those DIMM slots for DRAM. And we talked about that yesterday. How do I get my persistent memory in without sacrificing my DRAM footprint? Well, here is a potential way of doing that. Yes.
So this is not going to be subject to the CPU addressing limitations that we have in the Intel processors?
What, 48 bits?
Well, no. If you buy the cheap silver processor, you can't have more than 1 terabyte of address space. It's still going to be addressed like memory.
Correct. Yep.
That would still be a limitation.
Yeah, I don't know of that limitation, by the way. I know there's a hardware limitation in terms of 64 bits, and a certain number of those bits have to be used for other specific things in the hardware. And I think Linux has 48 bits for physical addressing. 52, yeah. So, as far as I'm aware, on Linux for Intel, you can support up to 2 to the 52. Now, there's going to be limits on where some of that memory has to live, but I don't think we're going to hit those limits with CXL. Managing these devices, managing any device in a system, especially in a cloud environment, especially in a cloud environment at scale, is very, very important to these people who are doing it. Go talk to Facebook and tell them you want to sell them a product that doesn't have a management interface. Do it, go. Okay, see how quickly you stay in the room, right? Go talk to Google about selling them a device that's awesome and can do amazing things but can't be managed at scale, and you will get walked out the door pretty darn quick, right? management at scale is incredibly important. Okay, we can manage NVDIMMs. They have an SM bus, and we can talk to them. But we can also manage PCIe. And in fact, one of the nice things about PCIe is cloud providers are used to deploying a lot of PCIe devices already. And so this is just another device that can align with that. And we can tie into other frameworks. So I'll get into this in a little more detail, but we have things like ACPI, which we use for discovery of devices at boot time. HMAT, which I'll talk about a little later, and so forth. And these are all things that we should be able to do within CXL. So this is another slide from this Compute Express link. Like I said, this is a public-facing document, and I'm going to have another slide after this that kind of digs into it. The really important thing about CXL, as we start looking at it in a little bit more, is that it's actually 3 different protocols that can be multiplexed onto the same electrical wire. So you can think of it as, okay, I have this electrical wire that supports PCIe Gen 5 and CXL, and basically I can mux 3 different messaging protocols onto that. And there's a mechanism by which that will be done, and there'll be a fairness algorithm to make sure that that kind of works. And there may be corner cases that need to be addressed and so forth. But there's basically 3 protocols that run at the same time over this bus. There's CXL.io. This one is PCIe. So over the bus, I can actually carry PCIe as it is with no changes at all. So that's very interesting because that's all my legacy stuff supported. Okay. I have CXL.cache, which is basically a cache coherent signaling protocol that allows me to take, as a device, to claim ownership of physical memory on a cache on my device. So if I want to basically be a cache coherent peer to the CPU cores that are in the processor, I can do that. And I can say, you know what? I want to own these physical addresses for the next 10 seconds because I'm going to number crunch on them. And I want to number crunch on them locally in my cache so I get the cache performance. And if you guys want them, you have to come to me and get them because I got them, right? And you can come and you can invalidate me and you can take them. But for a while, I'm going to own them. So that one isn't so interesting for persistent memory that we're focusing on today. But it's very interesting if you want to own memory and do operations on it. So as an accelerator vendor, this one is quite interesting for us. And then there's CXL.memory, which is basically the access method for if you have memory or persistent memory on your CXL device and the processors want to get at it in a low latency byte addressable memory semantic fashion, they'll use CXL.mem. Right? And all 3 of those protocols can be muxed on the wire. A CXL device may not support all 3, okay? But the processor should have the ability to support all 3 on any port that it declares is capable of CXL, okay? So now I can do all kinds of interesting things. So this is my CXL device, and I'm going to show some examples of this in a minute. I may have memory on my CXL device, and in fact, if it's an NVDIMM, then I certainly will, right? And that could be persistent memory, it could be backed up with a supercap to flash, it could be 3D crosspoint, it could be some other memory technology from another vendor, it could be a tiered hierarchy of different memory technologies where I present something to the host, but I actually use different types of memory to service memory requests against it. So maybe it's got an NVMe drive on it with some NAND, and I'm doing some kind of funky stuff, right? Interesting. And the host processor then can basically offload accelerator tasks, the accelerator. It can also access physical memory on this card, but it's not PCIe anymore. It's not mem-read, mem-writes. It's CXL.mem, which is designed to be low latency and higher performance. So let's break that down. CXL.io is PCIe Gen 5. All PCIe services will just work. So one that's very interesting for me is DMA, because I don't necessarily want my CPU to do 1 million loads or 1 billion loads in 1 billion stores, right? Why do I want to mem copy data around? We have DMA engines for a reason. Mem copy is a shitty thing for a processor to be doing, right? They should be processing data, not moving data. We have DMA engines for that, but we need to program a DMA engine. And for that, you need a driver, we have a very good protocol over PCIe for getting DMAs done. It's called NVM Express. Yes. Yeah. It is, yeah. For CXL.io, the packets are the same. Yeah, so what happens is you actually start muxing packets that look like traditional PCIe packets with other packets that have a different header type at the top. And PCIe 5, I think it may even be in 4, we've introduced a method of saying, I am a PCIe packet, or I am not a PCIe packet. And so now what a PCIe endpoint can do is it can discard any packet that's not PCIe. But what C6 and CXL are leveraging is the fact that I can now have packets on a PCIe link that can actually say to the endpoint, this is not PCIe. If you support it, do something with it. If you don't support it, return a UR or an error, raise an error, and we'll go forward from there. So now we can have multiple protocols on the same electrical wire, some of which is PCIe and some of which is not PCIe. I think that might be supported in 4, but it's being used by CXL in 5. It may not be supported in 5. The other interesting thing is if we have PCIe, we also have interrupts. We have MSI, MSIX. So now the accelerator can do a bunch of work. And if it wants to tell the processor it's done, it could tell it through CXL.cache or mem, but it could also just tell it through an MSIX interrupt, which we have support for today. If you want to do virtualization, we have SRIOV. All right, so now I can have virtual functions and I can pass them directly into VMs to be consumed at very good performance. VMware, you guys know a bit about SRIOV. ACS, address control, access control services, address translation services, these all work as is. You can almost think of it as I can now build a device which presents as a totally standard PCIe function, but then has other stuff on top through the mem and the .cache accesses. So the way to think about it is what this device would look like is it will look like a PCIe device, but it will also have other stuff on top of that outside of PCIe. And that could be additional memory that's in the memory pool, or it could be a .cache interface. And so having the ability to have a PCIe endpoint and then build on top of that with these .mem and .cache protocols is very, very interesting and exciting. And the fact that all this is supported by a CPU vendor that is probably the one that I'm going to be connecting to in my customer servers is, of course, from a business perspective, hugely, hugely important. Yes? For PCIe, you will, yes. So the interaction between the .mem and the IOMMU is somewhat architecture dependent. So that's going to depend on what the CPU vendor does, who implements that. But the thinking right now is that .mems will not go through the CPU, or sorry, through the IOMMU, because they're basically memory accesses. So they would just go untranslated. But anything to do with .io would interact with an IOMMU in exactly the same way that a PCIe device would interact with an IOMMU. Okay. Did that make sense? Yeah. Yeah, I know. Yeah. Okay, so again, this is the CXL slide. So these are some use models, and we're going to focus on the one on the right, but I will touch on the other ones. So, you know, what they're thinking is, how are people actually going to use this? Well, obviously, the processor vendors optionally can choose to implement this. Some processor vendors may say, screw this. This is like an Intel thing, and I don't want to be part of it, and you're all bastards, and I hate you. And that's their choice, right? That's their prerogative, right? But some CPU vendors will have CXL interfaces, and they will implement that. But I think, you know, more interestingly, for me at least, on the device side, I can safely assume that processors from a large CPU vendor will be available in the not too distant future. And I can do basically things like I could have an accelerator that may have a network interface out the back, right? And it may have cache, so I may have a cache on the accelerator, and I can now use things like CXL.io to write a driver for this in PCIe, but I can also use CXL.cache to pull in and own cache lines from the host memory and process them on the accelerator. And we cannot do that on PCIe today. The way you do it on PCIe today is you would write a driver that would actually lock some memory and say, this physical region of memory on the host, I'm going to copy that via DMA to me, I'm going to process it, and I'm going to give it back when I'm done with it. And if you need it in the meantime, you have to interrupt me, and we have to go through some dance, and it's all very painful, and it's all done in software, and it's not very performant, but it kind of works, and we kind of live with it, and that's what we're doing today. But .cache will actually say, I'll own the memory, and if you need it back, you just do a load or store against it, and you'll invalidate cache, and we'll have a little dance around. In hardware, we'll have a little dance around who owns it, and there's different modes for ownership, and then you can pull it back if you need it. Okay, so it's a very different hardware-supported path for who owns given cache lines in the physical address space at given points in time. Yes? No, they're the same. Yeah, and they're not my slides, so you can blame Clark Lender for that. They're his slides. But yeah, they're the same. I may have an accelerator that has memory on it. That memory doesn't necessarily have to be exposed to the host. So, as an example, today with graphic cards, a lot of graphic cards for AI come with an awful lot of high bandwidth memory on them. That is not exposed in its entirety by a bar, for example, right? We don't do that. So some of it's hidden and used by the accelerator, but some of it could be shown, right? So in this case, some of that HBM could be exposed to the host through the .mem side of things, and some of it could be exposed as a bar, and those two regions could overlap. You could do that. I'm not sure why you'd do that, but you could. Or you may expose none of it at all. And then this is the one I think we kind of care about. This is using, kind of forgetting about the whole accelerator side of things. This is what I would do to put persistent memory in my CXL-based system. So now I can have a processor. All the DDR can be standard DRAM. So I get my performance, I get my capacity, I don't have to worry about super caps that have to be connected to the DIMMs. I can have all of that as standard. And now I can take my CXL devices and they can have persistent memory hanging off them. And I can use cxl.io to write a driver for this if there's anything that I need from a driver perspective. But I don't even necessarily need that because cxl.mem and ACPI probably give me enough for this to come up as a memory device and be plugged into the memory subsystem of the operating system. And for this memory, which could be persistent or not, to be consumed by the operating system. Okay? And now I can do this on a processor that I really care about. So let's break down that rightmost case. This is, I say essentially an NVDIMM. Apparently, based on the definition of NVDIMM, this is an NVDIMM. Right? It's a CXL-based NVDIMM. But we're no longer constrained by the physical and electrical requirements of DDR and DIMMs. And I think that's very important. DDR is a very finicky protocol. It's a nightmare. And if you get it wrong, your server crashes and everything goes horribly wrong and dies, right? And we have ADR to worry about, and we have all bunch of, it's very, 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 very painful, right? It's a very wide bus, right? And it's not bidirectional. You have to multiplex, transmit, and receive onto the same pins, right? PCIe and CXL have a dedicated transmit wire. They have a dedicated receive wire. Form factors are much, much more interesting in PCIe. Even if you constrain yourself to standardized ones, you have low profile PCIe, you have full height, you have double width, you have power envelopes from 15 watts for small devices up to 250 watts if you want to add additional power, right? You have, the world is your limit when it comes to form factor. And of course, you don't have to stick to standard form factors. You can do all kinds of crazy shit, right? CXL.io gives me the familiarity of PCIe. I can write a driver. I can have a DMA engine down there if I want. I can use NVM Express if I want. I'm no longer consuming DIMM slots or channels. I can take all that capacity and all that bandwidth for standard DRAM. Of course, yes, absolutely. In fact, you could expose it 3 ways. You could expose it as an NVMe persistent memory region, which is essentially a bar that's persistent. You could expose it as a standard block device through the NVMe protocol as a namespace, and you could expose it over CXL.MIM, and you could have simultaneous access to all 3. There be dragons. You might want to have some kind of login mechanism on how applications access it, but you could do that, right? So now we have a beautiful world of block and simultaneous memory and simultaneous. And the reason why the PMR is interesting is because that, well, other devices may want to DMA into you, right? So you may want to have the ability to be a DMA destination, but CXL.MEM should support that. So if you have an RDMA NIC that's on a PCI connection, and it's doing a DMA to memory that's physically on the CXL device, that should just work. And you should say, I just want to set up a DMA buffer in some physical memory that just happens to be physical memory that's on the CXL device, and it should do a peer-to-peer DMA. It should not bounce through system memory. Right? And, you know, I've personally done a lot of work on peer-to-peer for PCIe, and we've submitted Linux kernel, or we've upstreamed a framework for that for PCIe. But CXL should support it almost natively because it's just a DMA to a physical memory address that's cache coherent. So that should be supported. So yes, we can start playing all kinds of fun games now. And now imagine also that you have a networking device on the back of this. Right now, you can fault in physical memory accesses from a remote location. So we're getting close to ponies here, gentlemen and ladies. We're getting close to ponies. All right. So a little bit more to think about. You know, the PCIe driver, we know how to write those. If we do have a DMA engine, which I think people, so certainly some people would like to have, then we want a way of programming that through a driver. We may want to add administration and management functions and other kinds of other stuff. We already have, my conjecture is we have a great protocol for this already. It's called NVM Express. So this is a slide that we worked on at lunch, so I need to acknowledge Andy and Dan, who both helped me kind of put this together. But I wanted to compare a DDR NVDIMM with a CXL NVDIMM. So if we look at the form factors we have here, DDR, we're constrained by the DIMM form factor. You know, server vendors are not changing that anytime soon. With CXL, we have many different choices of form factor. We can go with storage-centric things like U.2 or EDSFF, or we can go with the kind of more accelerator-based GPU, like we can do low profile. We can build our own. DMA, DDR in and of itself, you know, you don't put a DMA engine on a DIMM. That just doesn't work, no way to do that. You know, but in CXL, it's very straightforward to put a DMA engine on the device. Hardware virtualization, we don't have that for DDR. But CXL, we can use CXL.io and use SRIOV. Management, they can both be managed, but one of the interesting things is if you did align with NVMe management interface is a very mature spec, very well supported, and one of the interesting things is if I go to a customer, which I do, and I say, I'll talk about our products in a minute, we're very aligned with NVMe. If I tell my customer I'm managed by NVMe MI, they normally smile because these are the kinds of people who are already deploying tens, if not hundreds of thousands of NVMe drives in their data centers. So I'm just another NVMe device, and you manage me just like you do an NVMe SSD. Try telling a Google or someone else that you have this esoteric management interface you made up yourself, and you'd like their software engineers to integrate that into their million-node stack. And politely, they will show you, in fact, unpolitely, they will show you the door. Right? Their software engineers are very well paid and very busy. They don't have time to integrate your shitty code into their stack. Latency, good question. We had this question already. Latency is going to be a little bit platform specific, and I haven't actually seen any numbers yet. So, you know, I would go talk to Intel and ask them specifically if they have numbers yet and other people. But the idea is that the CXL.MEM access should be very low. Right, whether it beats DRAM, DDR, will depend a little on how it's wired into the internal coherent bus of the processor, but we'll see. Yes? Best case latency, well, we can put a kind of bound on it. It's going to be better than a mem read over PCIe, which is about a microsecond, maybe a little less than a microsecond. So if I do a 32-bit aligned or a 64-bit aligned mem read on a bar exposed on PCIe, I normally see numbers around 800 nanoseconds to a microsecond, and I think CXL.mem should do quite a bit better than that. So if we're down at like 300-400 nanoseconds, that's not that dissimilar to a DDR access, right? It has to go out on the DDR access.
Why do you think it's going to be better?
Because they're redesigning the protocol to get rid of some of the inefficiencies of the mem-read packet formatization in PCIe. So PCIe, there's a certain protocol that has to be followed before you can generate a message and send that message over the wire. The latency is not the electrical latency. The latency is the packetization and protocol latency. And CXL.mem is stripping out a lot of the junk that's in PCIe. So we're upper bounded by a mem read, and I think we're lower bounded by the electricals, which is probably under 100 nanoseconds. But I would expect it to come in well under 800 nanoseconds, which is getting pretty close to what you'd see on a DIMM anyway, right? Throughput we can put some numbers on because I know that if I have a DDR4 with an 8+1, so if it's 64 bits of data on my DIMMs and then 1 for ECC, which is typical in a server configuration, and assuming I get 80% efficiency and I clock this at 2600, which is like DDR4 best case if you're lucky on a good day, and probably never possible in a full capacity system, you're getting about 19 gigabytes per second per channel. Of course, you have lots of channels. If I have 16 lanes of PCIe Gen 4, and I assume that I can saturate in both directions at the same time, I can get quite a bit more than that. So bandwidth, I think we're good. And that's per 16-lane device. And I may be able to have multiple of those in a server. Right? So bandwidth is good. Latency is TBD, but I think we have potential for goodness. And that's pretty exciting. Linux support for CXL. Interestingly, if you go and grep the Linux tree for CXL, there is already a driver there. It's the OpenCAPI one. So that's not going to cause any confusion going forward. Yeah. Yeah, that's true. CXL, I think, is the CAPI one, right? Yes, thank you. That's a good one. There's OS. Yeah. So we're going to have some naming fun in the Linux kernel. But interestingly, you know, we don't necessarily need a tree, a CXL tree, but that will be something to be discussed, I think, over the next little while. But essentially what will happen is these devices will have an SM bus or an I2C interface. When you first power them on, what the firmware in the system will do is interrogate them through standard ACPI mechanisms. So they'll say, hey, what are you? And basically there's an entry to say, I'm a memory device. We have this extension for the ACPI called HMAT, Heterogeneous Memory Attributes Table, which can basically not just say I'm a memory device, but can actually give the system information about the attributes of the memory on that device. So you can say, I'm persistent. I have infinite endurance. I have less than infinite endurance. I have this kind of latency. I have that kind of latency. The firmware in the system and the operating system can make decisions on what to do with that memory depending on the attributes. So ACPI and HMAT get us both the capacity and also attributes of the memory. And you can make decisions either as the OS or as a system administrator on whether that gets put into the standard memory pool, whether it gets exposed as a device to be consumed natively by applications or something else, right? So basically, we don't need to do a lot of work in Linux to turn some of this stuff on. We can control who and how this memory is accessed. You know, one thing I haven't talked about is in a multi-socket system, we already know that accessing memory that's on a DIMM on a different socket is, you know, is not necessarily efficient because you have to cross the QPI in the case of Intel and the hypertransport or whatever it's called in the case of some other vendors. So we may need NUMA awareness. We already have that. We have NUMA control. It's user space library that allows us to make decisions depending on how close the memory is to the processor that actually wants to crunch on that data. Okay. And if the CXL device has a DMA engine and accelerators, then we may decide to also have a PCIe driver, and people can just write their own, or you know, we have standard drivers that we can use. And certainly, I'm pushing for NVMe to be part of that framework. Wow, we are running very late. I'm going to keep going for a minute. So some use cases. Volatile memory expansion. Somebody yesterday was talking about, I just need more F and DRAM in my system. This would let you do that. There is a big cloud company called Google who use power servers in a certain percentage of their fleet, and they use OpenCAPI to do memory extension, volatile memory extension. They just need more DRAM in some of their servers, and this is the way they get it. And obviously now they can do it with Intel processors, okay, using a chip like that. No need for persistence, just a bigger memory footprint, and obviously some NUMA control to make decisions about when you pull from that memory as opposed to when you pull from other memory, okay? Of course, that memory could be persistent, and suddenly you have an NVDIMM. We've talked about that already. We can go start building these things very, very, very soon now, okay? And of course, that volatile memory, or sorry, that non-volatile memory could be consumed as volatile memory. So it could be just cheap DRAM, right? So we can play that game as well. If we put an accelerator in this chip, this one here, then well, we can start doing DMAs, we can start processing the data, and we may even have a local cache. And if we have a local cache, we can use .cache to pull in memory from host memory, crunch it, and then return it using either the DMA engine or memory accesses. So we can start now doing some interesting accelerator things. We may have non-volatile memory here. This is kind of a computational storage thing now because we have persistence, we have compute, and we have them close together. And my conjecture is NVMe could be used to do some of the programming around that, especially when we add computational namespaces to NVMe, which is what we're doing. Now we get super crazy. Now I can have an NVDIMM that actually faults out to the network. Remote persistent memory. So now, you know, the gentleman from DreamWorks was talking about shareable flat address space. This could do that, right? And that may not be Ethernet. That could be Gen Z. That could be something else, right? So now I have the ability to coherently get out on the network from the processors I care about. Do I need Gen Z? Maybe I do, maybe I don't. Right, moving quickly, quick plug for my company. So we already do quite a bit of this. We already have PCIe endpoints that we can upgrade to CXL. Our big thing is we have a whole bunch of accelerator functions, including some we do ourselves, some that come from partners, and they're all driven by NVMe. So the great thing about CXL for us is it's a very minor upgrade to take our PCIe devices and turn them into CXL devices. What I need is support from the FPGA vendors to make sure I have the IP to go do that. We already deploy in interesting form factors, so you know these could be CXL devices. Right now they're just PCIe. I don't want to dwell too much on that. And they could have persistent memory on them. Where are we going with 2.0? So right now the spec for 1.1 is done. We're technically working on 2.0. I'm allowed to say this. I got approval to say this. It will align with PCIe Gen 6, which will obviously be faster, probably double again. It is going to address switching. So I've been showing you use cases where one device hangs off one port. If we can have switches, I can have multiple devices off a port. I can start doing peer-to-peer between devices, and I can even start doing all kinds of interesting things. We're not clear yet on whether that's a native PCIe switch. It's probably not. It's probably a PCIe switch with extensions to support CXL, but that's work in progress. And then we'll also add support for memory pooling, which is basically the ability for multiple CPUs to access a pool of devices that have memory on them and share that memory over that CXL network. So now we truly have rack scale composable memory infrastructure. Okay, so that I think is what the gentleman from DreamWorks was looking for. So the Holy Grail, where are we going? I'm going to finish up now. We want to go to a world where processors do loads and stores against a flat address. Basically, the world that we want is the world that DreamWorks wants. I want basically all the memory, all the data that I ever need in a flat address space, in my process's address space, that I just do loads and stores against. And ideally, I want a fabric that lets me do that. And I want OPonies, okay, so up there. And I need at least 74.4 bits of address space, please. So Intel need to make their address space bigger, because IDC tells me in 2025 we'll be at 25 zettabytes of total world storage. And I need to address all of it from a single address range. I want to be able to share all this data across multiple processes that are just doing moves or loads and stores. I do have a few problems. We have the physics problem. I don't know if anyone remembers Monty Python, but we do have this thing, the knights that say ni. They don't say ni, they say c, which is the speed of light. Yeah. At the end of the day, this media has a certain latency, and this fabric has a certain latency, and I can't go faster than light. So, you know, persistent memory needs to be low latency. So that's something we still need to think about. But I think CXL takes us on a step in that direction. And finishing up a little late, and then we'll get to questions. CXL may finally be bringing some clarity to the Star Wars of open coherent buses. Okay, I think it's great to have this defining moment where a big processor vendor has said, this is the way we want to do it. And fair enough, it may not technically be the best, and it may be a little annoying for some of the other people in the market, but it's a clear message, and it's an important message. Minimal software changes are needed to deploy persistent memory on CXL. Adding accelerators and remote persistent memory is possible, and we all get a pony. There's my thing. Yes.
Yeah, so you said 74 bits. Yeah. Now you have 3 address spaces, virtual address space, physical address, not shared across processes, physical address space, not shared across nodes, and this new 74-bit address space, whatever you want to call it. Gen Z calls it a Z.
Well, the virtual address space is one needs to be 74-bit. So that, yeah.
Is your basic premise of coherence. So there's the software aspect of that, sharing virtual address spaces across processes. This has never been done reliably or composably across lots of libraries and lots of applications. The other one is the real killer. It's the hardware aspect of coherence. Yeah. Requires invalidation, and eviction, and snooping of caches in cores, first level caches in cores, across whatever grid. You said 74 bits, so you mean the entire area. So sharing a coherent access to data across some large address space for lots of nodes is not going to scale.
So I think this, to be honest, is a little facetious. I think realistically, composability at the memory level is something personally I think should be done at the rack scale and not beyond the rack. But even getting to the rack scale would be awesome. And we don't really till now have a path to do that. But now we do. I can go and I can build something with next generation Intel processors that has a CXL-based fabric going up to a pool of memory at the top of the rack, and they can basically compose their memory spaces, their physical memory spaces at boot time, or even at live runtime.
Why not just embrace the scalability issue and abandon coherence and just treat this big shared pool of memory as non-coherent? In other words, abandon virtual addressing of it and just treat it like storage.
Yeah, I think that's even more complicated than fixing it in hardware, to be honest. And I think we can. So I think this is all going to work. This is all going to work at the rack level for sure.
I think CXL implies you have fully coherent, all memories coherent. If you have fully coherent,
But he's forcing the hardware to do a little bit of coherence. He's trying to stretch this fabric that can't scale further. And it just doesn't seem like, it seems like a waste of money.
I don't know. I don't know. I think if we make it consumable, which is what we have to do, I mean, we can solve it with no coherency now, but nobody wants to buy that because it's way too complicated to use as the end user. So at the end of the day, it's got to be something that people can consume. And I think that requires making it pretty much transparent to the end user and their applications that they now have this additional service. And I think, yeah. Yes?
So the innovation here is introducing new packet level protocols over the electrical PCIe. I wonder what is the impediment to having Gen Z or OpenCAP or C6 follow that same
The impediment is not technical. It's Intel.
So this could all be, well, why isn't it Intel for this one then?
Because Intel, this is the one they want to go with. And you'd have to ask their business people why they chose this one and not C6 and Gen Z. But it's a business decision as opposed to a technical decision.
So another processor, there's really nothing technically to stop other protocols from using the same mechanism. It's just if you want the coherence, and that requires requires processor hardware changes, so the processor vendor has to be a part.
Yeah. And there are other processor vendors who are doing things with C6 and so forth. The challenge from a business point of view is 99.99999% of the time, my product is going to connect to an Intel processor. So I can't tell my customer to go buy AMD if they're totally in alignment with Intel. From a business point of view, from a technical point of view, in a research lab, you can build anything you want, right, and do anything you want. But it's mass adoption that's really important here.
In the list of companies that have joined CXL, I didn't see Lenovo. Did you just leave it out, or?
The list I showed was the initial adopters, and the 75 companies. I'm pretty sure Lenovo is a member. Yeah, I'm pretty sure they are. Yeah, there you go. He's the man to ask. Yeah. And you can go on the CXL website, and they have a list of all current members of good standing. Yeah. Not yet. Working on that one.
What happens if I try to access a cache line that's in another server which loses power? And I didn't.
You want, so that would be in this case, right? Is it you're thinking? So right now, I mean, as I understand it, if you try to access a cache line in a different socket, or if you try to invalidate a cache line in a different socket, and that other socket has gone into either machine exception or it's lost power to that socket, your whole system is going down, right? Now, over to Fabric, certainly Gen Z, Gen Z is very complete around sharing, and they have cases where the bridge between the two devices can return an error code and say, basically, you try to invalidate that cache line, but I can't even get to that owner of that cache line anymore. It's yours. You can take it. I don't think right now CXL supports anything like that kind of complexity. I think the system would just come down. So basically, the device could bring the system down, but that's no different than a PCIe device bringing a system down now.
Gen Z also supports central memory, which does not go down with any nodes that go down.
Yeah.
So in other words, the memory stays up and all the nodes are down.
It would depend on how the slew protocol is
That's
written.
right.
Yeah, I mean, right now, CXL 1.1 is really a direct link between the CPU and a single accelerator that may have memory on it. It is not, CXL is nowhere near where Gen Z is, but at the same time, Gen Z is A, incredibly complicated, and B, not supported by any processor as far as I'm aware.
So it sounds like what you told me was that if the other server that you're sharing memory with goes down, you wind up going down as well.
Well, you can't even build that system with CXL today, and it's, I think it doesn't, CXL today doesn't scale, right? So in 2.0, they're working on the spec now. So I am sure they will think about that kind of thing. Gen Z has thought about that kind of thing, and they have mechanisms that try to prevent it. In reality, would it work? God knows, right? This stuff is tricky, right? And plus, nobody's built a Gen Z system at scale yet, as far as I'm aware. And if they have, they certainly probably haven't tried that kind of extreme testing of it. And then there's also, what does the operating system support look like? Like, is it going to complain, and so forth?
And not to go too far over my skis, but if you don't search for a cache line, you search for a memory address. If it's in cache and gets to you faster, then you get it.
I think the CXL example of what the gentleman just said would be if I, as a device, had claimed a physical address and I'm caching it on my cache, on my device, my CXL device, and I lose power and disappear, but miraculously the system hasn't crashed because of that, right? Which in and of itself is a bit of a challenge, right? What would happen if the CPU tried to invalidate that cache line? And to be honest, right now, I don't think the server would survive that particular event because that is basically a PCIe device disappearing, which can kind of work sometimes. It's called surprise removal, but it's not particularly nice even for PCIe, let alone for memory access.
But I thought you were talking about two separate servers accessing.
Well, this is the holy grail of PMO. This is where we may go over a long time. This is not where we are today. This is ponies, right? Yeah.
So it will limit is the idea. What's that? It will limit is the idea to merge this with DDR. I mean, you're effectively replacing DDR with CXL.
So I mean that's an interesting question. I mean, DDR, like JEDEC, have a roadmap for DDR, right? So they have a roadmap for DDR. Could the CPU vendors go, I am so sick and tired of DDR that I want to move to a different, more serial bus for my memory? Of course they could, and we've talked about that in the past, right? So power processors typically have a high-speed SerDes to a different chip that's the memory controller chip. So they already do that. Their processors do not have, some of their processors do not have DDR off the processor. They have a high-speed series SerDes that goes to a Centaur chip, right? We've had things like high bandwidth memory for a while. You know, some of the graphics guys no longer have DDR on their graphics chips. They use a serial bus to talk to, or they even put HBM on the same package as the chip, right? So you could certainly, I mean, it's not really a question for me, but there's certainly options, and there already have been options for a while around non-open buses or specific things a processor vendor could do to move away from DDR and DIMMs. But you know, the market still is very much in that place, and I don't see that moving away. Like I don't see the memory vendors moving away from DDR. I don't really see the processor vendors moving away. But that's a discussion to have with Intel's roadmap team and AMD's roadmap team and see what they're doing there. Yeah, but technically it could. Right? Technically it could. Whether it actually does or not. All right. But remember, this CXL doesn't support putting multiple DIMMs on the same channel and getting, you know, DDR has that capability, this doesn't. And yeah, there's good things about DRAM and DDR, but there's also bad things. Thanks very much for your time. I add into coffee time. Apologize.